9.3 is on separable equations. And so by definition, it says a separable equation is a first order. First order means there's only the first derivative in there. There's no y double prime. In which you get all the x's on one side and all the y's on the other. So here we'll be thinking of y prime as dy dx, and we'll think of dy dx like a fraction where we can multiply both sides by the denominator. So if you do this, the resulting equation will look like some function of y with a dy and some function of x with a dx, and then we just take the antiderivative of both sides. So it says this is really an abuse of notation. I should leave the dy dx and integrate both sides with respect to the same variable, but we would still, if we take the derivative with respect to x and integrate with respect to x, those kind of cancel each other out, but we'll always just think of writing it this way. So when we look at number 10, our variables are z and t. So we want to get z's, all the z's on one side, and get t's on the other. So what do you think our first step should be? I would subtract that e from both sides. So how are we going to separate? It's easy to multiply both sides by dt and get just this dz by itself, but we can't have z's on both sides. So I have to think of, how am I going to separate this? Well, right. So if I have like x to the fifth, I can separate that as x squared times x cubed, right? X squared times x cubed is the same as x to the fifth. I can break it up however I want it. So I'm just using this property, kind of x squared times x cubed equals x to the fifth. I'm using it backwards. So split that up as negative e to the t times e to the z. So that's just the property of exponents. When your base is the same, so you're multiplying like bases, you add exponents. And so say I multiply both sides by dt. Now I have the t's on the same side, and I want to get all of the z's on the left. So we can divide by e to the z. But it's maybe easiest to not have a fraction on the left-hand side. So how could I write it so it's not a fraction?
Negative z.
E to the negative z dz. And then the right-hand side will be negative e to the t dt. And if you want, I think it is a little bit nicer if we multiply both sides by a negative right now. So from here to here, just multiply by -1. So once you have the variables separated, that's why they call it separable equations, then just think of putting integral signs in on each side. So the right-hand side, the antiderivative of e to the t, this is just e to the t. And then the antiderivative of e to the negative z, so it would be negative e to the negative z, and we already have a negative there. So we just get e to the negative z, and then it doesn't matter what side you do it on, but you have to have a plus c on one of the sides. So I just always put it on the right. And I'm fine with you leaving it like that. WebAssign might ask you to solve for z. So I'm okay if you stop here. Once you get the antiderivative on each side, I'm fine, but WebAssign might ask you to solve for z. So if you were asked to solve for z, what would you do now? Yeah, natural log of both sides. So ln of e to the negative z equals ln of e to the t plus c. And the natural log of e to the negative z? Negative z. Can I simplify on the right? Can we do anything to simplify ln of e to the t plus c? Think of our properties of logs. So if we have ln of a times b, that's ln of a plus ln of b. Does that apply here? Do I have the sum of two logs?
Yes. No.
No, I have the log of a sum. So yeah, if it was the sum of two logs, you can rewrite it, but not the log of a sum. And then we have ln of a over b equals ln of a minus ln of b. But again, that's the difference of logs, and we just have one log there. And the last property is ln of a to the r equals r ln of a, but the c isn't being raised to the t power. So there's absolutely nothing we can do on the right-hand side to simplify. So our answer is just z equals negative ln e to the t plus c. Okay, let's look at one more. So this one we have an initial condition. So we'll worry about the initial condition last. I mentioned in the last section that we'll use this to solve for c, but that will be like our last step. That's after we integrate, and we'll get our plus c, and then we'll plug in that initial condition to find it. So our first order of business is to try to get the x's on one side, y's on the other. So I'm going to write y prime as dy dx. And so what would be our first step? Subtract y. Okay, now say we multiply both sides by dx. Then we'll just divide by x to get the x on the same side as dx, and we'll divide by y squared minus y to get this on the same side as the y. So we'd have dy over y squared minus y equals dx over x. Both of these things went in the denominator. So now all of the y's are on one side, all of the x's are on the other, and so we're ready to integrate. And the right-hand side isn't bad. The antiderivative of dx over x is ln. And I'll just put the plus c on that side. Now I have to think about how we want to integrate the left-hand side. So a u substitution is not going to work. And I wouldn't use a trig substitution because it's not y squared minus a squared. Integration by parts, it's not trig stuff. So what does that leave?
Factor y.
Right, so if we factor, I'm going to put the dy at the end, and we take out a y, we'd be left with y times y minus 1. So what method does that make us think of? Partial fractions. So we just have two factors in the denominator, so when we decompose it, there are just two terms in the sum, and they're both linear, just a over y plus b over y minus 1. And then multiply by the LCD, and we get a times y minus 1 plus b times y. And then what should I do? Y equals 1. And so we get 1 equals b. And what's the other thing we should plug in? 0. And we get 1 equals negative a. So we have the integral of, if 1 is negative a, then a is negative 1. So we have negative 1 over y plus b is 1 over y minus 1 dy equals ln of x plus c. And so now the left-hand side, those terms are easy to integrate. 1 over y, we know we get natural log. And what about 1 over y minus 1? Ln of y minus 1. And I'm fine if you leave it like this, but WebAssign might ask you to simplify. And so this uses that second property of logs, ln of a minus ln of b. So that would be ln of a over b. Actually, I should put absolute values on those. And then we could exponentiate both sides. So e to the natural log. So y minus 1 over y. Now the right-hand side. When we had the natural log of e to the t plus c, we couldn't simplify it. But when we have e to the natural log of x plus c, just like the way we split up e to the t minus c in the last problem, we can split this up. E to the natural log of x times e to the c. So we can simplify when it's e, but we couldn't simplify when it was log of a sum. So e to a sum we can simplify. And e to the natural log of x is just x. And e to the c, well, if c is a constant, e is a constant. So a constant raised to a constant, that's just some other constant. So the e to the c, we're just going to call that like a capital K. Everything there is a constant. And now let's just go ahead and plug in our initial condition now, and then we'll solve for, well, it's a K now instead of a C. So what am I plugging in for x? One. And for y? Negative 1. So we get negative 1 minus 1 over negative 1 equals k times 1. So negative 2 over negative 1. So the k is 2. So our equation is y minus 1 over y equals 2x. And you could actually get the y by itself, multiply by y, get the y's on the same side and factor, but I'm fine with this.